we introduce local connectivity-based density estimation for face clustering. Face clustering, which aims to divide enormous face images into different clusters, is essential to reduce annotation costs and can be used in many real-world applications. Given the set of face images, there is the corresponding face feature set extracted from trained CNN. Recent researchers construct the KNN graph with given feature set and estimate the connectivity between nodes using deep neural networks, where the connectivity represents the probability whether two nodes belong to the same cluster. In this work, we propose a novel clustering method which effectively excludes negative pairs from the KNN graph based on the reliable density while maintaining sufficient positive pairs. Also, we develop a pairwise connectivity estimation network to predict the connectivity of the selected edges. Figure shows an overview of the proposed clustering method. Given a KNN graph, a local connectivity estimation network, LCE-net, produces the local connectivity for each node, and reliable node density is estimated based on the local connectivity. Then, density-based and similarity-based edge selection are performed to exclude negative pairs from the KNN graph while boosting positive pairs. Finally, a pairwise connectivity network, PCE-net, determines whether the selected node pair belong to the same cluster. We employ the transformer encoder for LCE-net and PCE-net to effectively explore the relationship between each node and its neighbors. Given the KNN graph, where each node has k edges, it is inefficient to estimate the connectivity of all k pairs for each node since there are kn test pairs. Also, nodes on the boundary among different clusters are connected to neighbors with some false positive edges. To address this problem, we adopt the concept of node density, which links each node to the neighbor node with higher density. The existing density-based clustering methods compute a sum of similarities between a node and its k nearest neighbors to estimate the node density, which represents the measurement of how much a node is close to the center of the cluster. However, the similarity-dependent approach is vulnerable when k nearest neighbors are on boundary among different clusters. Therefore, reliable density estimation is essential to pair each node with a more centered node, and we develop the local connectivity estimation network to predict connectivity between each node and its k nearest neighbors. Local Connectivity Estimation Network, LCE-net, predicts connectivity between each node and its k nearest neighbors. We employ the transformer encoder to effectively explore the relationship between each node and its k nearest neighbors. For each node xi, we form a local feature matrix Fi by stacking its and neighbors' features. We perform the matrix multiplication to obtain a local affinity matrix AI. We use the concatenation of Fi and AI as the input of the transformer encoder to effectively exploit the relation between neighboring features. The encoder takes concatenation of two matrices and outputs an aggregated feature matrix F tilde. We copy the aggregated feature for xi, which is positioned at the first row in F tilde, and concatenate it to each row F tilde along the feature dimension. Then, the concatenated matrix passes through a MLP to estimate the local connectivity Cij for all j in neighbors of the node. For training LCE-net, we compose the ground truth of the local connectivity for each node. If two nodes belong to the same class, connectivity is 1, otherwise 0. We then train LCE-net to minimize a binary cross-entropy loss. For reliable density computation, we consider both the local connectivity and the feature similarity between each node and its k nearest neighbors. Unlike the existing methods, we use the local connectivity as well as the feature similarity to compute the reliable density. Based on the local connectivity, nodes on the cluster border can be assigned low density. We reconstruct a graph via edge selection. The reconstructed edge set is composed of a density-based edge set and a similarity-based edge set. For each node xi, we select neighbor nodes that have higher densities than itself to construct the said di. Among nodes in di, we select one node xj that is most similar to the node xi. We perform this process for all nodes to construct the density-based edge set. By selecting at most one edge for each node, it has the limitation that sufficient positive pairs cannot be selected. To address this problem, we additionally form the similarity-based edge set by connecting pairs which its combination of similarity and connectivity is higher than tau, where tau is a connecting threshold. We designed the Pairwise Connectivity Estimation Network, PCE-Net, to estimate whether two nodes, connected by edges in density-based edge set, are in the same class. Given a pair of connected nodes Xi and Xj, PCE-Net yields the pairwise connectivity Pij. To compare two nodes effectively, we use all features of their k nearest neighbors. We form feature matrices using respective k nearest neighbor features as done in LCE-Net. Then, concatenated matrix passes through the transformer encoder, which has the same structure as the transformer encoder in LCE-Net, to form an aggregated feature matrix F tilde-ij. Among aggregated features, we pick only two features at the first row and k plus 2 th row, which represent aggregated features for Xi and Xj, respectively. Then, original features and aggregated features are concatenated, and the concatenated feature is fed into MLP to analyze the connectivity between nodes Xi and Xj. When Xi and Xj are positive pairs, the ground truth of pairwise connectivity, Pij, is assigned 1, otherwise 0. Then, we train PCE-Net to minimize a binary cross-entropy loss. Table compares the proposed method with the existing clustering methods on 5 incremental numbers of test images in MS-Celeb-1M. The proposed method outperforms all existing clustering methods. The table on left shows comparison results of the proposed method with the existing clustering methods on the IJBB dataset. The proposed achieves the best performance on 3 test sets for both metrics. The table on right provides comparison results on deep fashion. Even though the proposed method is not the fastest model, it attains a good trade-off between the performance and running time compared to the existing methods. Figures visualize the embedding space, in which the features of 5 clusters are depicted as dots in different colors. We see that 5 nodes on the cluster boundary are connected to nodes with different classes in the left figure, whereas only one negative edge is selected in the right figure. Table shows clustering results on 3 datasets when PCE-Net or LCE-Net is employed to determine pairwise connectivity of edges in density-based edge set. We observe that PCE-Net is essential, even though LCE-Net can also provide pairwise connectivity between neighboring nodes. We proposed a novel face clustering method based on LCE-Net and PCE-Net. Thank you for listening.